You can see the meeting screen now, right?
Yes, sir.
Yes.
Just a moment to just. Okay. Yeah. Thank you very much for the invitation. I will be happy to actually discuss about our portfolio of our work and about the emerging low dimensional semiconductors. Mostly we focused on, recently we focused on 2D materials, 2D heterostructures, which have a wide range of applications in optoelectronics, including solar cell, photodetector, and also including quantum technology. So I understand the audience are undergraduate or master level students mostly, or few of them are PhD. So I will try to talk in more general sense so that it will wide reaching to several participants. And if some of you feel want to ask more question, we can discuss obviously at the end of this talk. So yeah, so here I will talk about though 2D materials. This is also class of low dimensional semiconductors. If time permit, I will give a very quick overview of the other low dimensional semiconductor that we worked also in before. Okay, for sensors. Okay, so here you can see that nature of work is how, because how we can control or manipulate atom down to is few atom thick semiconductors. That is the essence of this today's talk. Okay, so obviously this thrust area is sort of new generation of ultra thin materials, right? Because we all are now passionate for electronic devices, right? So we all have smartphones, we want to do smart things, we want to detect our blood pressure, everyday activities, and monitor our our blood medical reports. We can transport to these appropriate devices that can give a record of our health conditions. So flexibility is one of the extent. So for that we need semiconductor, because many electronic devices that rely on semiconductor, right? So some semiconductor have to be flexible, but silicon cannot be flexible. Also another addition is transparency. So transparent and high performance. You can imagine day to day the amount of data you are collecting, so it is enormous. So or also information we are, the device is collecting is enormous. So that for that, how much, how whether we can for high performance can be done. Okay. In addition to ultra thin body and devices, right? So we can think about now whole world is, you can go anywhere, you can find Wi-Fi signals, right? Whether we can harvest this Wi-Fi signal to to power some of the small IoT type of devices or flexible electronic devices, or you have smartphones, other thing, whether we can power it, we don't need to charge it frequently. Okay, so the message is, so there is a proof of concept type of devices using this kind of 2D heterostructures, where we can get this Wi-Fi band of radiation, we can convert from AC signal to DC signal. So it can be again flexible. So there are possibilities to harvest others in the source of energy to self-power or to develop self-power devices. That will be amazing, right? A lot of electronic devices we can charge it that way. So day-to-day number of electronic devices are increasing, or Internet of Things, where we can remotely control or wirelessly control many electronic gadgets. So we can think about household devices, starting from the small calculator to light bulb. Now we know that we have smart light bulb that can tune the frequency of emissions. So that that need different range of power that it consumes. Also, you can see that personal devices, the mouse, the smart watches, and mobile smartphones, Wi-Fi plus memories. These things are also personal devices are increasing. Like our smartphone are getting smarter because we can do computation and memory and many things we can do with smartphones that with a similar to a computer. So there are different kind of wireless communication protocols are available with the range of energy consumptions. So there are also power density. There are different range of devices like indoor photovoltaic, outdoor photovoltaic source of energy are available like thermoelectric or body heat that can be also provide some energy, but you can see the power density is very low. So there can be piezoelectric, that means you can work mechanical energy you can convert to electrical energy. So that is possible because heavy like vehicles or when we walk, sometimes we generate a lot of mechanical force that pressure can be generated to electrical energy or triboelectrics. But outdoor photovoltaic definitely have a more useful power density for to address many devices. But indoor photovoltaic like we have all lights in malls or you can see departments is 24 hours sometimes is growing. Suppose you have point of view sensors or detectors, whether those can be also charged by these indoor photovoltaic devices. For indoor photovoltaic device, the ideal photovoltaic or energy range is 2 electron volt, whether outdoor photovoltaic, the ideal range is 1.4 electron volt. So you can see here there is a different type of material is required for different type of applications. Why I'm talking about the Internet of Things is this is a big chunk of devices we are going to use in the next 10 years. So it is projected that by 2035, so there will be 1 trillion interconnected devices is expected by 2035, which is now it is almost 1.6 trillion devices almost in is expected by 2025. So to sustainably powering such Internet of Things devices, it's really a grand challenge humankind have to face or do it. So in addition, you see why it is a challenge, the energy consumption by electronics. If you see it, this plot, the device sells per year, sells in millions spare parts per year. The projection you can see that the smartphone sales of smartphone is increasing drastically because as I told, smartphones are becoming more smarter as compared to laptop and desktop or tablets, because tablet also increased and saturated, but smartphones are becoming more very handy tool to do most of the work like checking email, sending all these things, even notepad. You don't need to now need any right things. So many things can be done with smartphone. So as a whole, the power consumption or energy consumption of all these electronic device, you can expect is almost double by 2022, and it will be expected to triple by 2030. It will consume almost 1700 terawatt hours of power energy consumption is required, which is equal to the entire total electricity consumption of US plus Japan in 2009. So obviously there's a huge amount of energy consumption is going to happen, required for to power only electronic devices. So more is roadmap. So that is also we can see that in order to accommodate the daily uses of this amount of data, we eventually need to handle with the many computer. That's why a lot of focus are going on now for quantum computer development, or even if for quantum computer at the same time, computer cannot be work in for ordinary use. For smartphone especially, what we need is more number of a transistor whether we can incorporate in a small chip. So if you see the Moore's laws that trends like that, So there was a time there is a happy scaling was up to 2005 or 2010. After that, there are other part one have to work on so that for these to incorporate a more number of a transistor in a small chip, because in conventional semiconductor like silicon and germanium, when you are thinning down, because of the 3D nature, they have a lot of dangling bond that introduce a lot of scattering, and the thermal dissipation, their mobility, other factor drastically goes down. Okay, so it is hard to actually make the transistor on and off below certain thickness. So though there are other strategy like FinFET and the FinFET and all gate around kind of structure geometry also people used upon. Still, there is a lot of challenges where conventional semiconductor we cannot thin down. So if you check this, oh sorry. So check this conventional silicon or germanium or silicons or germanium based semiconductor. If you thin down below a certain thickness like 5 nanometer, their mobility drastically reduces. So it is almost not useful for electronic devices. Whereas there is other class of semiconductor that recently picked up from 2015 onwards, where like graphene like material, graphene is not a semiconductor, that's why its application in electronics reduces. That's why other semiconductor like tungsten selenide, diselenide, molybdenum disulfide, tungsten disulfide, like this class of 2D semiconductors gain momentum because their mobilities are still preserved even at below a 1 nanometer thickness. That's really amazing. This is a whole lot of research is lot of people are focusing on this class of semiconductor to make again emerging devices. So this is in terms of carrier mobilities, and this side is showing thickness. At all are done at room temperature. So that's why you can see that there are still progresses going on in this direction to integrate more number of a transistor. So because of the limit now, whether you can see you can heterogeneous scaling where you can combine silicon technology with 2D devices. So because 2D devices are naturally, yeah, they have dangling bond free surfaces. What you can see here, 2D device are there. They have weak van der Waals interaction between different layer, so that it is easier to peel a single layer, and they don't have any dangling bonds on the surfaces. That's why roughness or scattering related issues of 3D semiconductors can be mitigated while using 2D material as a channel material instead of silicon. Also, 2D metal, the van der Waals nature of the SO silicon oxide insulator like interface can be realized, where leakage current reduction can be also realized, even though you are, because of the short channel effect can be avoided, even though you are reducing the channel thickness to 1 nanometer. Okay, so there are also another addition is this layer material depends, sometimes their band gap can also vary, that also one can tune easily with this 2D material, their energy band can be tuned. So that's why all in one in future we need memory and sensing computing together at one devices can be realized and in one day using this kind of hetero integration of silicon to 2D materials. So this can be also good for quantum computing. This is the future we are moving towards. So whole of our talk will be mostly focusing on this kind of 2D semiconductor, which is one layer of a transition metal sandwiched between two layers of the chalcogenides like sulfur selenides. So that gives very extraordinary semiconducting behavior. We'll discuss subsequently. So why size matters? Why when you are reducing the thickness to a single layer, why their properties changes? Why this is very interesting? Let's think about. What is 2D material in common sense, or because 2D material concept was it was not that much, but 2D electron gas was known from decades. Right. So this is where conventional semiconductor, like you can make quantum wells, like one type of semiconductors, you sandwich another B semiconductor, B with very fine, very narrow band gap, so that you can form different kind of heterostructure. If it is confined, you can form a two-dimensional electron gas system. And that how the nature of a charge transfer, all these can be depend upon the type of a confinement. Mostly in the 2D materials, the confinement is in one directions, so that electron can only move in XY directions. So it's a 1D confinement lead to 2D 2 degrees of freedom for the carrier to move on a plane, so that's called two-dimensional system. But it was there in the 3D semiconductor, but it was physically confined. But now we can realize that 2D semiconductor without any physical confirmation by other without making any heterostructure by 3D confinement. Okay, so one can do 1D confinement same way of zero-dimensional confinement. If you confine the carrier from all directions, that's what your quantum dots are. Okay, so they have unique density of states. That density of states talk about what are the available energy state to assess for particular energies landscape. So advantage is in understanding this 2D nature or type of charge transfer. So yeah, we are realizing that device miniaturization, we are thinning down the device size. So because of the quantum confinement, it is new material behavior or new phenomena sometimes emerges. Of course, we are also increasing the surface to volume ratio. If you want to a smart sensor for gas sensor, a toxic gas sensor or explosive sensor, this can be fabulous because with a small molecule that can alter the surface charge density. This is why it can be act like a sensor to detect very small minute amount of things, a response. The response can be electrical, can be optical, can be chemical, or by other thermal or any other means. Okay, so how can develop such sustainable technology, so efficient technology? One can use 2D materials or their heterostructure beyond graphene. That's a hope. So because this 2D field now is self-sustainable, it can find almost all type of material that's required to develop 2D semiconductors or 2D chips. So let's give a very common examples of 2D materials, because imagine if you want to make a thin slice of 3D layer. So if you have a potato, you have to chop it into, literally chop into to make slices. But if you have onion type material, we can just peel off one layer. This is exactly the way Novoselov and Andrzej discovered the graphene. So from a highly oriented graphite, graphite HOPG, so they can able to, with a scotch tape, they can able to peel off a single layer of carbon chain. And that single layer was found to be is a rich information it contains, which is completely different than its bulk counterpart. But between these layers in graphite, there are van der Waals bonds, because there is no certain strong bond. Van der Waals bonds are weaker. We can see that they are short range order of 10 to -6, distance to the -6, whereas covalent crystals, their bonding between different layers are very strong, which is order of 1 by R. So that's why Coulombing forces are very really stronger than the van der Waals attraction. That's why it is easier to peel up a single layer of materials from layered semiconductors or layered materials. In addition, what we can see here in bulk semiconductor, if you zoom into the surfaces, what you see here, the surface have a lot of dangling bonds. Dangling bonds are which are not saturated, because the bond have to saturate its, suppose the one bond have to connect with several atoms. Because atoms, those are on this finished on the surfaces, there are still some bonds are not saturated, not completed. So those can be called as active sites for other gas absorbers, other things to oxidize. This is how you put a piece of iron, other thing that can be easily oxidized, not a graphite. Graphite is very stable for a long time because the bonds are saturated on the surfaces. So that is fantastic because this when you try to deposit metal for to make electron device, because of this bond sometime they can oxidize, they can add some additional factor for in the electrical conduction. So there are different kind of semiconductors so far realized. One is graphene type, which is semi-metals. It's not like pure metal or semiconductor. It's semi-metal. We'll discuss at some point. And boron nitride, which is an insulator, and these are the semiconductor, molybdenum diselenide and phosphorine. We'll discuss about this. So the journey for 2D materials start from carbon, because carbon was an amazing material. It can found in all many forms. You see diamond that many people is fond of, because diamond now can be also synthesized in the laboratory, because diamond is a perfect insulator. But if a graphite is a good conductor, but this carbon can be in terms of fullerene. This is a zero-dimensional material. It act like quantum dot. Whole the size of this ball can be order of few 1 nanometer or few nanometers. Or we can form a carbon nanotubes. There was a time this was a very hot topic. The carbon nanotube, carbon can be act like a tube of a few nanometer diameter that can give ballistic transport, because carrier can go from one end to other by without any scattering. So it can be ballistic transport. One day ribbon under this Nobel Prize what we got with graphene, a single layer of a carbon chain, and that because of this is called sometimes Dirac material. The valency band and conduction bands are touched at a point, so carrier can without scattering can transfer from conduction to valency band. That can give ballistic transport. And these are many semiconductor where people are thinking about replacing the copper as interconnect with the graphene. It can give a 1D channel, as well as it will, lot of heat dissipation problem can be solved, because it's obviously transport characteristics. Now our technology reached a level where we can grow this kind of single layer of carbon up to 30-inch, and sometimes we can get roll to roll these graphenes. We can already, there are some company already making these graphene rolls, graphene epoxy PET rolls, one can get it. So some other company also trying to replace this display with graphene, at channeling materials. So there are a lot of progress is going on this graphene in terms of application, real world application. And there is a program in Europe, there's a graphene flagship program where a lot of people, lot of groups in Europe coming together to realize the lot of applications of graphene in many various range of application fields. So in terms of seeing the broader prospect, so for communications or for display, so we need a large, very wide range of communications. NIR, you can NIR communication, night visions, mid infrared regions. So we can see ultraviolet light, visible, infrared, microwave to radio wave. Different band of the electromagnetic radiations have particular applications, right? Microwave to radio wave. Especially we'll focus on many devices for optoelectronics. We are focusing mostly visible light. This is a very narrow region if you check the whole spectrum, available spectrum in the universe. But this is where many important or interesting application optoelectronic device focuses on. So in that aspect, what we can see here, 2D materials community is sustainable in terms of we can get ultraviolet band gap regions if you use hexagon boron nitride. The 2D layer band gap is more than 6 electron volt. It can deep UV region we can access. The visual region, there are a lot of other semiconductor MOS2, WS2. They are determined by its band gap. Electron band gap is the gap between valence band and conduction bands. Okay, so this maximum of the valence band and minima of the conduction band, if they are in the same wave vector or space, momentum space, they are called direct band gap. Okay, so that is very essential because your quantum yield, other things will be good in that sense. But graphene, because of the special Dirac nature of its band gap, what you can see that their ballistic transport, so that is very, it can assess almost from infrared to radio wave or terahertz regions. This is also, that's why graphene, there are a lot of interest are going on in terahertz applications, where with low energy, millielectron, sub-millielectron volt levels devices can be realized. Okay. We will discuss more focus on this semiconductor part, which is band gap lies in the visible region. Okay, so as I told, 2D family of materials now within a span of 10 decade, 1 decade, so we can wide range of 2D material are now discovered or they are predicted by now. So there can be 2D chalcogenides, semi-metals, 2D magnetic materials, 2D ferroelectric materials, 2D semiconducting, perovskites, like many more, 2D oxides, 2D hydroxides. There are many class of 2D material now emerged. So as if this, we can feel is another territory where a lot of things to explore, because it takes again several years or decades to explore completely all these materials. That's why this community is getting stronger in terms of new finding in the day-to-day life. Okay, within this field of materials. Okay, so we'll focus our talk on these layer transition metal dichalcogenides, TMDs, which are especially in the form of MX2. M stands for molybdenum or tungsten, and X stands for the selenium, sulfur, selenium or tellurides. So if you check the bulk layered materials, they are in the form of the structure, because you see it, this here, whatever, the other one is inverted triangles, like here. So that's why the unit cell of this TMDs are just a two layer, and that two layer repeat in space, right? So, but it is allowed to peel a single layer. That because of this single layer can be peeled off, that means the single layer is a half of the unit cell. So because of this lack of, this symmetry is breaking, inversion symmetry, that give rise to very interesting properties of this 2D layer material. And from top view, if you see it, it looks like graphene. Instead, the carbon, it can be alternate materials of molybdenum and sulfur or selenium, like that. They form hexagonal rings. So barely a unit cell thickness is just 1.2 nanometer. And if you take a single layer, it will be just 0.6 half a nanometer. That's why the half a nanometer semiconductor give very extraordinary property. If you check the band structure, that what we discussed in bulk, the valence band maximum, conduction band minimum, there are different K point, different momentum space. So, but if you thin down to a single layer because of the quantum confinement, there is a rearrangement of the electronic band structure, and we get a direct band gap at a K point, where, so that means what you can see here, many materials in the bulk, their band gap is lower. When you thin down to 2D regime, so their band gap increases. That connection from the hollow to field symbols. So it's because of the quantum confinement, this some band profile can change. This is interesting because imagine your bulk, lot of bulk materials have low quantum yield, but in terms of optoelectronics, if you thin down the material size, it will become more brighter in terms of emissions. That is interesting, which is not for conventional semiconductor. In addition, this class of semiconductor, the valency band is very unique. They are splitted. They are, there is a splitting of a valence band exists. That means, in addition to electrons charge and spin, another one can we add into the system is called valley. Because of this, either you can access this valley or the second valley. Transition can be two times. So that means we have a lot more possibility. We get 3 degrees of freedom to manipulate the system more efficiently. So that's the emergence of electronics valley Hall effect possible because of the unique band structure of this class of material. Okay. So in addition, in terms of excitons are mostly the bound electron hole pairs. When in 3D semiconductor, when you are exciting an electron and it will leave a hole behind, so this electron hole form a bound state. Then once they form a bound state, they have a very small short life. They can move on the surfaces. So you can see that exciting states are just below the 3D band gap. Okay, and 3D, this exciton, because of the dialectic and the presence of other structures, the bonding is very weaker. But the moment you thin down the single layer, what happens because of the reduced dielectric screening, the electron and hole pair see more because of the strong Coulomb interaction, the binding energy can be stronger. They can be well separated excitonic state well below the band gap of the 2D material. That is very interesting because compared to this semiconductor, the excitonic transistors can be realized that have more secure transitions and more narrow emission one can observe if we can harvest excitons. Also, exciton can be formed trion, another three particle system, or bi-excitons. They are more, useful for if you go for more like quantum computing or single photon emitter. All these things, this will be more interesting. Physics can be, or in device can be realized in future. Also, they can form other kind of trion polariton. The energy state can be again tuned by choosing appropriate substrate alone. If you put a particular substrate like tungsten dioxide, strontium dioxide, and titanium oxides, so the energy state of the trion can be tuned. Imagine in future also this excitonic based transistor can be realized. When you make vertical heterostructures, you want to realize a very thin excitonic transistor. That means you want to say the light or excitons have particular binding energy that can diffuse and come back. But if you imagine we want to photonic crystals where you want to send the light, your thickness of the channel material should be comparable with this light emission. But here, even if atomical thin sample, you can transport the exciton and get that light out. So we can make ultra thin photonic, or smart transistor using this concept. Very recently, this kind of 2D semiconductor can stack another 2D semiconductor. We can also control a lot of phases, lot of physics, new quantum emitter. All these are emerging in this field. Okay, going to the heterostructures. So if you see for metal, the band structure overlap. For semiconductor, there is there is a valence band, conduction band. When you shine light, electron move to these states. If you put another semiconductor with a lower band gap, and if you take another, then there is a potential energy barrier for this electron to jump or this electron to hold to move uphill, electron to jump downhill. So if you have another A stacking, and if this is thin enough, then you can realize the quantum states, quantum well structure. So you have, instead of continuous energy state, you have discrete energy level. So at a particular energy time, applied voltage, for certain applied voltage, you only can assess these states. So localized emission can be realized, or tunable emission for. So that way you can make quantum wells. For superlattice, the barrier layer have to thin enough so that adjacent electronic wave function can superimpose, can form this kind of mini band. So these are good for like you can realize very high efficient solar cell. Here, electron and hole can be effectively tunnel from one layer to other layer, so that efficient charge extraction can be happen. Because many solar cell, the charge can be excited, they can combine again very quickly, recombine very quickly. So to avoid that recombinations, we can make this cellular structure. But it's easier to grow one layer by layer on semiconductor. But for 2D materials, it is really challenging job to observe layer by layer like superlattice. It's still a challenging job. Okay. This is where our expertise is. We discovered that how we can make this layer by layer structure in lateral geometry. So if you check the heterostructure of different type 1, type 2, type 3, depending on the relative band alignments. If the bands are like that, confined one well between two, it can be good for laser, high electron mobility transistor, light emitting diode. In this class of band alignment, it will be good for solar cell or exciton. So type 3 band alignment will be good for tunneling field effect transistors. So it is essential that for if you compare the bulk semiconductor based PN junctions, the carrier can either go by diffusion or drift because of the presence of effective depletion region. And the moment you try to do atomical thin PN junction, you see your material dimension is already thin enough, is 1 nanometer roughly. So that there is no more extended depletion region. All the carrier transport process occurred by tunneling, which can be occurred in ultra fast process. So which is less than 1 picosecond. You can imagine ultra fast charge transfer can be occurring when you make this kind of heterostructure. And 2D material community, you have a lot of 2D semiconductor there. You can, if you want a particular specific application, you can choose a library from the library of 2D material, which combination you want to form heterostructures, which give you a particular specific applications. Okay. So far, to the field is, it will become very easier because a lot of 2D material you can just exfoliate. So imagine if you want to exfoliate this much stack of boron nitride, MOS to boron nitride, MOS to again boron nitride, graphene. It is a lot of effort because it can add contamination, many issues. It is good for proof of principle based devices, but not for scalability of for larger application. Of course, there are recent progress is there to grow this kind of structure in MOCVD to again you grow individual material, then stack them in this order. But however, to make perfect planar interface, mechanical exfoliation is not a solution. If you want to specially separated PN junction heterostructure truly in the 2D geometry, in the quantum regime, so you need to grow them directly. This is where we have made several progress in these directions. So now we'll talk about this lateral heterostructures. This is called in-plane heterostructure or lateral heterostructure. So in the 2D metal, you can make either vertical or lateral heterostructures. They have different, excitant binding energy of this heterostructure are sometimes comparable to the vertical. But you can truly realize a 1D geometry, right? One-dimensional channel when we are combining two lateral interfaces, where it is predicted that excitant binding energy can be stronger even because of the strong coupling between different regions. So binding energy can be stronger even from their vertical or pure materials. So this exciton this carrier can be, because of the lateral geometry, once you form excitons, they can be coupled with the other energy sources like surface plasmon. They can be transported easily through these lateral dimensions. In terms of devices, many systems require that when you have to really make a 2D transistor or diodes, so you make that you have to manage the thermal energy. Very recently, one group also shown that using lateral directions, it also act like a thermal rectifications. Thermal management, the heat can flow in a certain manner stronger than the other directions. So simultaneous electrical or thermal rectification is also possible using this geometry. In addition, the Kaustav Banerjee group, they predicted that when you have lateral heterostructure, the sub-threshold swing, that is a parameter decide how easily, efficiently you can turn on transistors. That is determined by sub-threshold swing. And that is limited by thermionic emissions, which is really 60 millivolt per decade for conventional semiconductor. We cannot go down because that is the threshold. But if you make this 2D semiconductor, so that can the sub threshold swing can even go to sub millivolt per decade, so which is amazing. But nobody have realized that. That would be ideal for simulating our brain or neuro-inspired computing or this kind of tunneling field devices. So that's the future. We can make lot of computation with a low power consumption and with more efficiency. So also there are many interesting physics where amount predicted when you combine materials in lateral geometry. Okay, so now, so lot of introduction I gave about heterostructure. Now we think about how we can manipulate this kind of structure, how to make the structure. There are two ways one can prepare the materials. One is chemical vapor deposition, one of the challenging methods as compared to mechanical explosion or solution based. Because this is the only method where we can make a very high electronic grade structure. Solution based will give more polycrystalline type of structure. So I think this is what we develop this method where we can systematically grow this kind of high quality crystal using CVD, chemical vapor deposition methods, where we can grow them these lateral structures in side by side. We can grow MOS2, then on the side WS2 against on the MOS2. So we can grow this kind of structure directly in the CVD method. This kind of structure, we showed that there are very strong light matter interaction characteristics. Also, there are very interesting exciton based domains one can realize is a photoluminescence mapping. Also, what we demonstrate the strong nanoelectronics like a small PN junction diode, photovoltaic light emitting diode using these atomical thin samples. So there are many new discoveries are also awaiting when you combine this material in this geometry. So there are a lot of challenges in this field. What we develop, as I told, a very robust CVD method where you can see here beauties. We can grow all them in lateral. We can selectively grow in lateral direction. We can control this channel width and we can make super lattice as well as we can band tune it. We can show you subsequently. So how to grow them? This bigger challenge is grow this kind of structure. Chemical vapor deposition is one of the method where is a very scalable, low cost strategy where we need a high temperature furnace. Okay, so this high temperature furnace and we can put the 2D precursors. Precursor, suppose you want to grow molybdenum or tungsten, you have to put precursor related to molybdenum tungsten. Then you put this precursor at a higher temperature and you control them by your carrier gases from argon, hydrogen to nitrogen and pure gases. You switch between the carrier gases. So we can deposit selectively this precursor on your substrate which are placed at a lower temperature zone. So there are a lot of dynamic involved that mass transport. This reactor gas can go either gas phase reaction occurs or it can be surface absorption. Then this byproduct can react and these things can be diffused on this substrate and that can give rise to 2D layer. All these byproduct can go away from the outlet. It can be. So why it is growing on 2D now, why it is not promoting 3D islands? Because you imagine these materials are van der Waals material. The surface are not, there is no saturated bond on the surface, but the edges are free. the edges. That's why the materials prefer, the incoming adatom prefer to connect the edges. So this is how they can grow in the lateral directions. So this preferential, this is sometimes called edge epitaxy. So we heard about epitaxy because it follow the surface pattern, right? But this material adatom follow the epitaxy of the edges. So this is how one can make this kind of structure. So there are a lot of critical parameters in CBD methods that play roles. We are part of this book where 2D materials, electronic sensor devices, we contributed what are the current strategies for 2D metal synthesis. There are several parameters that can control the growth, like substrate, type of substrate used to grow, temperature, pressure, precursor pressure. But if you keep on changing all these, you will not end up anywhere. But the point is, what we focused on, we fixed all of the parameters. We only vary the carrier gases. By only varying the carrier gases, we can control absolutely atomic scale dynamics of this carrier gas, precursors. So in our method, we use two types of carrier gases. One is with the water vapors, another with hydrogen. Water vapor act like a oxidizing agent, hydrogen act like reducing agent. For molybdenum sulfide to tungsten sulfide based lateral heterostructures, what we use is we put together bulk precursor one at one place, we just switch the carrier gas. And we put the substrate at the downstream. So you see, when the presence of water vapor, only the molybdenum domains are grown on these structures. When you switch to the argon and hydrogen, then the molybdenum domain stop growing and the tungsten domain grown on the edges. This is very simplistic because there is a long story behind it. It's not that easy to control. But what we can see that because switching between these two, one can realize molybdenum, tungsten, again molybdenum, and you can see a very, very well-defined crystals, 2D heterostructured crystals. Because when it is a crystal, this is grow in a particular direction, and you can see the sharp edges. And this is the molybdenum, tungsten, molybdenum, again tungsten. Domain can be grown. Long story short, we can see that water vapor as helping the molybdenum regions, but tungstens are there is a dynamic between the oxides that form when water interact with the both molybdenum and tungstens. But molybdenum oxide is more volatile, grow only. But when you switch to hydrogen, only the molybdenum deplete molybdenum oxide sulfides, they are deplete to molybdenum that will not evaporate. But there are a lot of preserved oxide from tungsten in the previous step that contribute to the growth when you switch to hydrogen. Okay, so this is how by switching the stage 1 and 2, one can create this kind of multiple junction heterostructure. In addition, one can control the temperature of the substrate. That means you are control the kinetic coefficient with slightly higher temperature, the edge energy. This edge energy barrier one can overcome. This is how one can concurrently grow a bilayer. Like monolayer, one can grow a bilayer of a lateral heterostructure using this strategy, same strategy. So now couple of slides will show how we can characterize this kind of structure. So you can see that if you have monolayer, because of this metal have strong dielectric constant and absorption, even a monolayer, bilayer, the absorption is very distinct. So we can see a monolayer, bilayer, trilayer, they have distinct absorption. We can directly see it in the optical microscope. Even if you buy one Amazon, one simple microscope on the, there also you can easily visualize this. This is very fantastic, right? You don't need sophisticated technique to see a monolayer. So this is, but especially we need a particular thickness of the SiO2. This typical 285 nanometer, there you can see this structure very prominently. We don't need any microscopy. So Raman spectroscopy, another tool where Raman method means you are shining a laser light, it is going to the carrier from one to virtual state, it come back. So it leaves some energy, vibration energy states that give a fingerprint of the material characteristics. I'm not going deeper into that topic, individual characterization, what exactly. So we can see that you have a lateral heterostructure, middle molybdenum diselenide, tungsten diselenide. So what we can do, take a spectra from here, molybdenum that look like this. So we have a peak around here, and silicon peak is always into 521 around for both the cases. For you take a spectra, record a spectra at this position, you get a spectra around like that. And if you choose this spectra and take a mapping of a whole the surface and choose this spectra, then you can see that only this position or this metal present only within the triangle in the middle region. So that corresponding to your molybdenum selenide. If you choose the other part, so in this region you can see the only 250 centimeter inverse, that is only tungsten is present. So Raman and photoluminescence mapping give a clear picture of the presence of different material in this. So then you take a position, no matter what you do, you take whole spectra from point by point from whole region and check this position map, position of the more intense peak. So we can see also that way distinguish the presence of different crystalline boundary within the. Okay, so you can, with our method, we can make even 300 micron crystals of multiple periodic junctions. You can see the sequentially age epitaxy of molybdenum selenide, tungsten selenide, molybdenum selenide, tungsten selenide in multiple junctions. Again, with a Raman PL map, we can characterize this material on photoluminescence. So you can see the presence of individual tungstens and the molybdenum selenides within these lateral heterostructures. So it is fantastic, but to see the crystallinity. So as I told in the bulk materials, it is easier to use the XRD, X-ray diffraction or other technique to characterize. But when you literally have a monolayer thick, it is very difficult to get good diffraction peak in that. So for that we need the HBNI electron microscope, where the wavelength is picometer. So electron, you collect information from this high angle annular dark field, whichever electron that scatter more. That means that give more Z contrast. Means this G contrast means atomic contrast. This is using this method you can realize the honeycomb lattice, right? If you have monolayer, you can see this in the 2D projection of your 3D materials or 2D layer. So two layer are sandwiched between one point. This triangle, if you see it, it looks like that. But at the end, you can get a representation of this hexagon here, So that typically represent you have grown a very honeycomb lattice of single layer. Also, another advantage is this material you can use simple water or polymer, you can detach, or with a polymer layer, you can transfer this material to any arbitrary position substrates. So like here. Okay, so we can put on a hollow, this is a hole in a carbon grid, there you can place the lateral heterostructure. And using that high-end angle annular dark field microscope, you can see the lateral interface at this point too. You can see the tungsten diselenide and molybdenum diselenide, and we have perfect atomic interfaces. You had a PN junction. This is especially a PN junction, which can give perfectly one-dimensional interface at ultimate thickness limit. One can take a photoluminescence map between multiple junctions, and we can realize how these atomical sharp junctions or diffuse junctions are transferred between one while moving from center towards outer sides. So yeah, I'm just skipping with the interest of time. Yeah, this because of atomic junction can play a role in the charge transfer dynamics. So with the sharp interfaces, it can prolong the photogenerated lifetime, carrier lifetime recombination. That can be useful for lasing or diode or optoelectronic devices. So similar way, We can also fabricate molybdenum sulfide, tungsten sulfide lateral heterostructure. We can get a very fine photoluminescence line maps. Also, we can control the layer number within the lateral heterostructure domains, superlattice, because this is very interesting in terms of they have a very unique photoluminescence scattering. In addition to A excitons, direct band gap emission, B exciton, we can get also indirect excitons in bilayer. So we can get perfect also see here perfect atomic interfaces between bilayer of tungsten sulfide, bilayer of molybdenum sulfides. So this method also allows us to tune if you mix two different chalcogenides. So far we are mixing molybdenum selenide, tungsten selenide. If you mix sulfide or selenide heterogeneous precursors, chalcogenide precursors, it is also allow us to systematically band tune the individual interfaces material and still you can make lateral electrostructure where individual domain can be tuned the amount. So that expand the spectrum of available 2D material one can realize one can tune between 1.5 to 2 electron volt continuously and still maintaining the heterostructure. Okay, so there are a lot of predictions. One can make quantum dot within the lateral geometry that can be useful for qubits. That can be spin valley qubit can be realized. That can be good for quantum computing. So in our method, we can realize very fine lateral hetero interfaces less than 100 nanometer up to 50 nanometer we realize. So this is a photoluminescence map using FMT. One can see that we can see that localized quenching of emissions. So one can get features up to 10 nanometer regions what is localized photoluminescence behavior within the lateral heterostructures. I'm just skipping these slides with the interest of time. Okay, so now we'll cover the device parts. So there are many devices people have demonstrated so far. We have again a review article from recent review article. We compile different applications of 2D heterostructure in energy harvesting, flexible devices, photodetector sensors, spintronics, twistonics, thermoelectric device. But I will focus on photovoltaic and light emission characteristics in this. So there are advantages, disadvantage in 3D semiconductor, as I mentioned in the beginning introductory talk is, so there is a 3D material because of the dangling bonds, there is a mobile charge center. So we need a lot of gate voltage to modulate the charge carrier in this 3D channels. Because when you thin down this material, the mobility decreases with the thickness of the order of thickness to the power 6. Where band gap also increases by a square of the thickness, e.g. T to the power 2, is below critical thickness of 5 nanometer roughly. So this is typical IV characteristics where one can get the soft threshold swing. This steeper this value is, the larger the on-off ratio is, and the lower the soft threshold swing, the better the efficiency of the device. But imagine if you have a 2D semiconductor, so with the oxides, so we can easily modulate because of the reduced dielectric screening. So with the less gate voltage, we can modulate these carriers in this channel because one of all the things can be faster and more efficient as compared to 3D semiconductor. But there are still critical issues of contact because you remember this material don't have very dangling bond. So, contact become a bigger critical issues. Either you can create selective edge contact and top contact. You can imagine what are the difficulties. You try to contact, especially at the edges of the 2D semiconductor, it's really difficult. So also to choose appropriate dielectric and top gate, this metal is very 1 nanometer thick and it's very sensitive for the device fabrications. So in addition, you can see that the 2D material can add another van der Waals contact. Because of that, the tunneling barriers can also form in addition to Schottky barriers. But that way one can find the right combination of material, you can slightly allow, find a right combination of 2D material that can mitigate this kind of additional barrier that form because of the van der Waals nature. So a lot of work is going on this direction. I am not focusing on. So a lot of contact engineering is a big issue for 2D material community. There are several groups are working on this direction to find a right combination of material or to make the 2D transistor viable for large scale applications. So we try to combine several materials. 2D materials are different form. There can be 2D 3D integration or 2D lateral geometry, monolayer, heterogeneous 2D 2D TFT. So what the critical point is for practical applications, one need a on-off ratio of the order of 10 to the power 5 to 10 to the power 8. Mobility should be greater than 1000. SS value should be less than 60 millivolt. And more important is device stability, reliability is also bigger issue in the 2D material because many 2D material are very air sensitive, they cannot sustain. So these are the critical challenges still exist in 2D material for real world applications. For whatever material we fabricated lateral heterostructures, like we can, so to assess the property, you can see that it's not just in schematical, it's very easy to show it, but practice we grow like that, conformal. If you want to assess the inner domain, you have to run through that. That's why we need to cap with the insulating 2D layer like HBN to isolate it, this short circuiting these channels so that you can assess by electron beam lithography the inner channel. By the outside channel, you can assess the characteristics of WSE2. If you measure these two electrodes, you can get the properties of MOSE2. If you measure between these, you get properties of WSE2. If you measure between 4 and 5, you get the characteristics of these lateral hetero interfaces. In fact, we did that, and the first thing to check is your ohmic behavior. So if it's the ohmic behavior, that is your IV cassette should be linear. That means 1 and 5, it is linear, and between 3 and 4 is also linear. So there is no circuit barrier present between your metal and semiconductor. Second thing is you apply global gate bias. So see that we apply more and more bias. You then check which channel is the conducting at which gate bias region. For WS2, mostly negative gate bias region, this channel is conducting because you have been applying negative gate bias. So most of these, because of the p-type carrier, this almost after a gate bias minus 20 volt. The WS2 channel is conducting. For MOS2, this is conducting in positive gate bias. So that indicate MOSE2 is a N-type semiconductor where WSE2 is a P-type semiconductor. Imagine. So we are directly growing PN semiconductor on these things. Unlike silicon industry, to make PN, you have to selectively dope particular region. To make heterointegration, this gives a lot of challenges to selectively dope certain region. But we can somehow, intrinsically grow this direct PN junction. Okay, so once you know you have a PN junction, then you can make photodiode. You apply cyan light, then photo light there are a lot of some depletion region at the interface. The electron hole can recome, it can separate it out. Electron can go one side, hole can go other side. This is how we can extract photocurrent. Your IV characteristics you take at zero emission is like that. When you increasing the power of the light, you can see the monotone, the increase of current, drain current, increasing the power of the light. And we extract the on-off ratio of the order of 10 to the power 5 to 10 to the power 6, which is typical, comparable with the existing silicon technology. So that means we can, in terms of quality, we are growing very high quality PN junction structure. Also, with sulfide selenides, we can get photovoltaic. Since PN junction diode is there, so in photovoltaic, when you shine light, So there is an inbuilt potential developed at the interface that very immediately separate the charge carrier. So that means you measure the short circuit current without any gate bias. You measure the current as a function of emission of light or illumination of light onto this channel. So we can see that by increasing the power to 9 microwatt, your short circuit current increases. That essentially gives the, talk about the photovoltaic effect. That means one can realize atomical thin photovoltaic devices using these things. So same thing, it can do a dual job. Same, it can use as a photosensor, electronic circuit, or transistor, and it can be modulated by your light, right? It can be light-driven transistor. So that can get fancy, or there can be hybrid concept can be emerged. Also, we fabricated when you have a lateral heterostructure. So we have a PN junction. You inject electron hole from this respective source and drain, and they can recombine and emit a light. So same thing when you have PN junction, we have all possibility to demonstrate. So here you can see that energy of emission, and here is the gate drain to source voltage you apply. After right amount of voltage you apply, you can see emission around 1.85. So 1.85 emission around here. Okay, so that means you can think about, you can make atomical thin light emitting diode using these structures. So if I can take another 10-15 minutes, I can show the one-dimensional semiconductors. So like 2D semiconductors, show that one can do, we can pattern the metal electrode metals in a regular arrays, and you can grow semiconducting nanowire. This act like a water bottle. We in a childhood we heard about story of a crow throwing stones in the water pot and the water level rises, right? Same thing happens. Water here, the gold disc act like a semi-liquids, and the semiconductor indium phosphide, when you put on that, the crystalline and the bottom and the semi-liquids of this water droplet mixture goes rise up. This is how we can create arrays of semiconductor nanowires. You can get semiconductor indium phosphide nanowire, also heterostructure you can see here with the different doping. So this is a gold at the tip. You can make regular arrays of nanowires using this technique. So nanowire, there was a time nanowire found many interesting applications in photodetector, single cell endoscopy, because the size of the nanorods are 100 nanometer. You can probe to a single cell and see the dynamic there. You can make logic gates. You can make nano LED. This all around gate, and lasers, nano sensors, a lot of things where people demonstrated. Also, we demonstrated nanowire can be used as a sensor, biomedical sensor. Because you imagine these nano channels are, semiconductor will not detect any biomolecule selectively. We have to functionalize this surface with a particular chemical and a particular biomolecule, so that it will be selective to particular biomolecule of interest. Suppose you want to sense the virus, so you have to find the antibody or something which can be coupled to the virus. So if you can, and you can figure out how to antibody or that antigen, how we can connect to the nanowire. So a lot of chemistry actually involved here. Then what the science is here is, when you have a selective molecule attached on the surface, that is change of electric field here, electric current in this channel. Since the nanowire diameter is very small, so the minute change in electrical signal can change the conductance of this channel. So this is how we can detect molecules up to down to femtomolar level, single molecule level. We can also one can detect. Of course, there are challenges in fabrication, all these things. So as a point, indium phosphide nanowire, you can form different kind of linking molecules, so that you can form, this different kind of molecule. You can see there are several layers of functionalization one have to do, to selectively detect DNA, protein, other things. So one can do a lot of lithographically, a lot of multiple channels, so that in one chip we can detect protein, DNA, other viruses. So that you have 64 electrode with a microfluidic, we can inject this channel and you can detect by fluorescence or by electrical measurement. Okay, so another few motivational topics that are we alone are the only intelligent species in Earth to harness nanotechnology. So that is you can see, so bacteria, if you, there are a lot of things you can get in literature on YouTube, but one thing is simple bacteria. We have infection or virus, right? Throat infection, kidney infection because of the virus, we take antibiotic, bacterial infections. What that does really, they generate some nanoscale type of polymer. Okay, so that nanoscale polymer that can propagate, so that that can act like a glue that attach to a surface, and this is how then after that they slowly divide into different colonies. And very interesting is a very fundamental science as well. These colonies, once they grow, they can also communicate between these different molecules. There is sometimes called coherent sensing. They can sense by genetics of molecules in different colonies. Like we have different villages, colonies, we communicate by our things. So there is some communication between different domain exist, and they spread the colony, then they can form bigger biofilm. The point is, once the biofilm is formed in the critical size, it's very difficult to remove it. This, then we have to take antibiotic to break these polymer chains, right? So this is very fundamental to understand as a physicist. What are these, to understand underlying forces involved in this. You can use these semiconductor nanowires. Very fundamental. What you can see that when you shine light onto it, so when bacteria try to sit on the surface, they can try to, because size of the bacteria are even bigger than the nanowires. So the when bacteria try to grab it, this can bend the nanowire. So it can mechanical cantilever. Depending on the amount of bending, one can extrapolate that amount of forces involved. That will be in the order of nanonewtons forces. So if you have very high-end confocal microscope where you can focus your light cone to a particular hundreds or 200 nanometer region, so one can probe these regions. So this is exactly what we did is we have nanowire arrays and bacteria. We try to live bacteria. These are not live bacteria, but these are live bacteria. You see that bacteria moving on the surfaces, and we can track individual bacteria how they move. And now we can track also individual bacteria move on the nanowire arrays. But you can see that change of position of the dots. So we can feed that dot with a circle that can track the change of diameter position, so that we can detect the deflection in the order of 10 to 20 nanometer. So that way, then we can extrapolate that deflections to amount of forces that bacteria impact on particular nanowires. Also, we can make a three-dimensional real images because you can make Z scan. So you see that how bacteria colony form, what is the nature of this porosity, all this. So this is a very fantastic world to see, how nanoelectronics or nanomaterial can sense the fundamentals of life, right? So we can stack them, understand these steps involved in that. So in addition, we can learn many things from the nature. So we can learn self-cleaning, we can learn mechanical properties of from nature's mosquito eyes. So we can learn beautiful photonics from the nature like peacock or butterfly. So how this metal, photonic materials arrange the gaps, how the color emerges. This is another fantastic thing anyone can guess. This is a creature, right? Inside this ocean floor, what you can see here, if I click, this is like a squid. That in 3 dimension, it changes camouflage, right? It changes body shape, size, and color that to the surroundings. This is very fantastic. You can think about the young generation. So whether you can develop certain material that can mimic in 3 dimension, not only its the physical body, but also color and texture of the surface. This is especially nature of this kind of granular that within the screen that can contract or they can expand, that can allow certain amount of light to reflect on the surface or trap. So this is how we manage to change the
Mimic
picture.
mimic. Biomimic.
Yeah. So we can see here the squid camouflage. You can different kind of this things are available so that selectively change the light, all these things. So one can think about making real world application is evolve like this, trying to make jacket which can mimic this kind of color. Okay, so that can be waterproof, windproof, and change color when exposed to light. That made out of 2 billion glass pairs. So also 2D material, many now hidden cameras are there. So you already say selective where we can make three-dimensional photo detector. So that is also possible and that will be flexible. So that kind of core things are also now coming by using these 2D semiconductors. We can make 3D photo detector in all, location specific, all this. There are hybrid things are coming into picture. You can mimic from nature and can do that. Okay, so my take-home message is the future technologies demand that if you can combine different kind of electronics, optoelectronics, communication, memory, sensing, memory, computing, all together in a 3D integrations in a more hybrid platform. Okay, that means we saw that in one slide, there are a lot of plenty of 2D material family are now discovered, and you have many ways to combine them, and we can realize a lot of different territories, even that we have not realized in 3D semiconductor. So, yeah, the summaries. So, before going to take any bigger role of the semiconductor in application, so finding a good method to grow them with scalable strategy is very essential. And another factor is stability, reproducibility, device to device variation characteristics. That have to also have to done in a more cost effective manner. Now you've seen that many smartphones or something are very becoming cheaper. If you try to fabricate some very fancy, very good semiconductor, but then if its price is too high, it will not going to market. So you have to find some very easy method like we grow only just using semiconductor, we grow with the help of water and hydrogen alone without any sophisticated technique. It's a very
बोलने का तरीका वो अंकल के जैसा नहीं लग रहा.
So we can control the interfaces, we can make multiple periodic junction, we can make superlattice, we can control the alloys. So we saw that these are also promising material for low power optoelectronics. And there are a lot of scope by combining different materials. One can assess we can do work on future quantum technology, one can do in that direction. Sensors, health monitoring, low power electronic display. We can make ultra thin optoelectronics, indoor lighting, smart mobile devices. There are a lot of scope of combining these materials for future technology. So I acknowledge my previous groups and some collaborator. I'm a recent collaborator. And also my group and funding support from DST, from Quantum Mission, and from startup funds and from my recent group and PhD scholars. And thank you very much from IIT Kharagpur. I will be happy to answer your question if any.
Thank you very much, Professor, for very informative and interesting talk about basic physics of 2D material and its synthesis to device application. Now the floor is open, and I request to participant, please unmute yourself and ask the queries to Professor Sahoo.
Chandravan, if you could allow me, can I ask a few queries to Professor Sahoo?
Yes, sir. Yes, sir.
Okay,
yes,
thank
yes,
you.
sir.
Thank you. Thank you so much, Professor Sahoo, for the wonderful talk. And it is very interesting talk, because now it is the age of 2D semiconductors. Right? Along with the world, also India is also in the mission. In the recently launched India Semiconductor Mission, also 2D material is probably the heart of the innovation. So now, Professor Sahoo, since you have vast experience in this particular material, So I'd like to know from you that even if you said like 2D materials, for observation we can do using simple microscope. But
Hmm.
once you would like to fabricate any devices, then
Okay.
basically you probably would be requiring electron beam lithography or laser lithography.
Okay.
Now your device dimension, if I could recollect, like you mentioned, monolayer, two layer, three layers. So even
Hmm.
if those triangles you have shown, I think the size may be in the range of 10 micron to 40 micron one side.
Yeah, yeah.
That means in order to make a contact, you need some precision lithography.
Yeah, yeah, that's for sure. Hmm.
So, the question is like, there may be a solution that if we can establish uh, probably an electrode at the bottom, like just on top of silicon oxide, and then
Hmm.
try to deposit monolayer and try to have a top contact. Like if we would like to avoid the usage of precision lithography. But then there will be a problem because this monolayer is synthesized at very high temperature. At
Yeah,
high
yeah,
temperature, these contacts will be damaged.
yeah,
So
yeah.
what is your say? Because you mentioned like even if we have simple microscope, we can observe that is true, 100%.
Hmm.
But then what about device fabrication?
Yeah. So from device aspect, of course, because of the lack of time, I didn't elaborate the discussion that part. So there are a lot of challenges again, as you mentioned. Lithography. Okay, when we go down to very thin channel, even silicon technology that need also electron beam lithography, because they can be done in a mass scale, right? 12-inch wafer in that's what it is feasible. But definitely that is if your electrode dimensions are more than 2 micron, laser lithography can be done or photolithography. If you want to fabricate your mask using a laser writer, then you can do photolithography. Routine pattern devices can be done. That is pretty easy. A lot of people are doing that. But if you want very short channel devices, definitely one have to approach through the electron beam lithography. There is no other solution at this moment because or interferometry lithography, which can go up to 100 or 200 nanometer to 3 500, some micron level. But below 100 nanometer, definitely one only approach is electron beam lithography. There is no other solution.
Because in that case, like even if let us say electron beam lithography is not available in one's institute, so the sample should be shipped, for
Yes.
example, to
Mhm.
the collaborator's lab. But there will be the issue that how long this 2D material will sustain during shipment.
Yeah, you can, there are vacuum sealing are there. Simply you can buy from market this, food packaging we get, no meat package or food, dry food package. So there are some vacuum sealer is there. We used to do with that. We buy some vacuum sealer. You just seal your sample, you can just sell it. So that works. Several months it can stay there. So it's not an issue at all. Only problem is humidity. If you keep it for outside with too much humidity, that degrades over time. But again, one have to understand there are, this field is not again mature. There are a lot of understand why this is degrading. Because in ideal it should not degrade. If you form a perfect semiconductor, this top surface there is no dangling bond. Humidity cannot attack. Humidity only can approach from the edges. Somehow you can find some saturating the edges, and the top surface, we make very high pure crystals. Then lifetime can be expanded. But you can see many electronics devices, there are a lot of packaging, right? You do a layer, another layer you have to stamp. So that way it is embedded within the structure, and that issue will not be there. So, so your semiconductor, once you fabricate, pack it, it will be okay. Only then if you are exposing the surface to outside, then this issue of stability can come. But then some people can coat with a boron nitride layer. Boron nitride is transparent, then it can protect the underneath semiconductor layer from degradation.
My last query to you, Professor Sahu, is like there has been paper published on silicon oxide. Few
Okay.
papers probably is obtained in which people have tried different layer of dielectric to grow this 2D material. But is there a publication that people study that why silicon oxide, or let us say aluminum oxide, is the most suitable dielectric to grow this 2D material, like the basic physics behind it?
Yeah, I think it's something to do with maybe the surface roughness as well. No, if it's too rough, ideally these are van der Waals material. They can grow almost because if some people also grow on metal like copper or also gold foil also some people grow. So because this is the growth mechanism, these 2D are different from graphene. So because this is why we prefer the nucleation is another controlling factor, right? Once you manage the nucleation, then don't follow the surface pattern. It can follow the edge if it takes. So for to control nucleation, one have to play around. This can be also, there is a critical nucleation size exists, right? Thermodynamic barrier is there. So whether the nucleation will exist or will dissociate back to the gaseous phase. So that energy of the substrate also plays a role. So that's one have to play around the atom flux ratios of between the transition metal and chalcogenides and temperature, precursor amount, pressure. So there again the number of variable increases when you want to play around different substrates. So ideally one have to optimize that parameter. I think it can grow on many substrates. But one
Thank you
have to
so much.
find, one have to hit that critical, combinations.
Thank you so much, Professor Sahu, for the
Thank you,
wonderful
thank
talk.
you,
Thank
Professor.
you. Thank you.
Thank you very much, Professor Mukherjee, for asking valuable questions. Now, I request to participant, if you have any queries, you can directly ask from Professor Sahu.
Hello. Good morning, sir.
Yeah, good morning.
So I am Mayank Dubey from IIT Indore. Sir,
Okay.
first of all, thank you for this wonderful presentation. Sir, I just wanted to know in the first part, you discussed about the Internet of Things. So,
Okay.
if we wanted to integrate this 2D based photo detector that
Hmm.
you have suggested, so how that integration will be going? Like, how will be integrating this 2D heterostructure based sensor and this Internet of Thing application, this physical integration, how we can achieve that?
Okay, so yeah, we have to make some, it's a prototype device again. You have to make a device of photo detector. Then you can, lot of DIY project is there. No, so we can try to see that how can signal, we can connect with it. Or suppose you want you have a photo detector, very low power photo detector, and you can combine a small chip in addition to that with the breadboard, all these, Arduino, all these things are many electronics guys
Yes.
can understand. So you can integrate in such a way that part of the daylight you are getting, that light you will, there will be some energy storage you have to do also. One photovoltaic device that can store energy. There can be very minor small battery that can store charge. Whenever it is required, it is charge the photo detector or
Yes.
sensor, hydrogen sensor, anything. So that can be couple of things can be combined together, right? Of
Yes.
course, some electronic expertise is required to combine different fields.
Okay. Sure. 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 Okay. Thank you. Thank you, sir.
So, Professor Sahu, can we take the question from chat box?
Yeah, you can read it.
Okay, okay. So, in the chat box,
Say,
first question.
I cannot see that. Okay.
Okay, okay. So, first question from Anandya Bose. Why lateral heterostructure is preferred over a vertical heterostructure? Is it more advantageous for sensing application?
No, it is not that way. So yeah, each one have their respective, individual advantages. Vertical heterostructure, a lot of work have been done. Okay, so that is also one. But you see, vertical structure, you don't get a perfect interface. So you don't, suppose you want to study the pristine nature of the charge transport, you cannot know it. When you have a specially separated 1D junction, you know exactly, suppose you have photocarrier dynamics, you can exactly probe how exactly carrier are transporting. In terms of exciton, other things. So for fundamental science, the lateral heterostructure are not that common. It's not that easy. You just mechanical exfoliator to realize a lateral structure. This is again another territory. A lot of gray areas are there to explore fundamentally. And of course, there are some limitation. In lateral heterostructure, your amount of interface is very low. You get only 1D channel. You have vertical heterostructure, you get a very 2D large area, right, of interfaces. So if you want more carrier to obtain, vertical heterostructure can advantage. Suppose you want to channel the carrier in a specific way, then lateral heterostructure can be useful. So I guess it will more systematic, a point of use, or depending on the scope or the type of application, one can think about whether adopt lateral geometry or vertical geometry.
So, Professor, another question is related to the grain boundaries. Is grain boundaries play a role in memory?
Yeah, it can be. Grain boundary can play a role in memories. Yeah, but we are not looking at that aspect. But it is definitely there are some report grain boundary can play some memories. But in my opinion, this grain boundary related things is very difficult to control and very low threshold or efficiency one can obtain rather than to figuring out a right way to do memories, because ion migration have to happen, so one can think about more robust way. But of course, suppose you are making some devices with the PN junction, you have a junction or boundaries is there, whether that can also act like a memory, in memory, in addition to electron dimension. One can also see that possibilities.
Another question from the chat box is, a graphene can be used to boost the induction or capacitance of sensor that uses the principle of induction and capacitance for detection?
No, graphene induction, there is paper, but graphene mostly helpful for interconnects. Because see, between different, if you take a cross section of the chip, so you have different layer of things, right? So where copper or aluminum mostly used. So copper, aluminum have their intrinsic resistance. Because of that, the heat dissipates. In mobile, if you work or play video for over a time, it heated up, right? Because of the management of the heat dissipation is not efficient. But because of the intrinsic resistance, since graphene have a ballistic transport, the carrier can transport without generating sufficient heat efficiently. So the heat dissipation, because of the accelerated transport, your resistance is reduced or carrier can be transported efficiently. So heat dissipation problem can be mitigated. So in my opinion, graphene will be more useful for interconnects. People are trying to use it. It will be a good, fantastic material for interconnect. It can replace all coppers.
Okay, thank you, Professor. Now I would request to our team member, please thank our speaker. Sumit, please share the slides.
Oh, I can stop it, right?
Okay.
I stopped it already, right? Yeah.
Yes, sir. Yes, sir. Binu, please start.
I would like to thank our speaker. Thank you, Professor P.K. Sahoo, for enlightening and entertaining session. We are grateful for the time and efforts you took to share your thoughts and experiences with our IEEE community. I also thank our sponsors, Excel Instrument, Sincel International Private Limited, Optimized Solutions Limited, Rudraksh Technologies. I also thank all the audience for attending the session. Thank you.
Thank you, guys.
Thank you, sir.
Okay.
Thank you, sir.